Hey everyone, I just thought I'd start up on some problems from chapter 14, and I'm starting off with example 14.9 or something very closely related to that. Specifically, this problem I worked online during class last week, but there was a careless mistake. I forgot to divide one of the constants out or whatever, and ended up getting a slightly different result. So I thought I'd work it again from the beginning and sort of better explain it. So let's go ahead and share my iPad screen and I'll show you how to solve this problem. But it seems to not have taken. I don't know why it's not working. There it is. All right. So as you can see, I've taken the liberty of copying a little bit from example 14.8 as well as putting in 14.9, so it's a little easier to read. But the problem is as follows. The spring stretches 0.150 meters when a 0.300 kilogram mass is suspended from it. That same spring and mass are moved to a horizontal frictionless surface, and the mass is pushed to compress the spring 0.100 meters from equilibrium. In other words, x0 is equal to negative 0.100 meters, and the mass is given an initial velocity in the positive x direction of v0 equals positive 0.400 meters per second. What is A, the phase angle, B, the amplitude, and C, x of t, the x is a function of time? So, what we're starting off with here is the fact that we know this is a simple harmonic oscillator. So it fits the equation of the form x double dot plus, let's say, some constant A times x is equal to 0. And when you have that particular equation with that particular constant, the solution is x is equal to a cosine, and that is the cosine of the square root of whatever that a constant is times t plus the phase angle phi. So that's the general solution. In the case of a harmonic oscillator that is actually the harmonic oscillator with a mass on the spring, then A is actually the square root, or A is actually K over M. So in that case, we get X double dot plus K over M. X is equal to 0, and that means X of T should equal A cosine omega T plus phi, where omega is defined to be the square root of K over M. So you notice the way this was worded, they gave you a spring stretch as well as a mass that was hanging on it. That's the typical code word for telling you to, hey, figure out what the spring constant is, and then we can go ahead. So we'll start off with that. What we know is F is equal in magnitude to K times X. In this case, the F is actually 0.300 kilograms, but that is a 0.300 kilogram mass hanging from a spring. And the mass, of course, is 0.300 kilograms, but the weight is mg, and that is given by 0.300 kilograms times 9.80 meters per second per second. Uh, and that's all equal to K times the amount of stretch, which is 0.1, oops, 0.150 meters, like that. So it turns out you can compute K by taking zero point 0.3 times 9.8, which I think is 2.94. 0.3 times 9.8, yes, 2.94. newtons divided by 0.150 meters, which gives me 19.6, and that's newtons per meter is the spring constant. So we now have the spring constant, and with the spring constant, we can go ahead and compute omega. So omega is equal to the square root of k over m. So that's going to be the square root of 19.60 newtons per meter divided by 0.300 kilograms. And when I do that computation, I get the square root of 65.33. And notice that turns out to be kilogram meter per second squared is a newton divided by a meter, that's a kilogram per second squared. And then divided by a kilogram, that just gives you a per second squared. So this is s to the negative 2 power. And I'm obviously carrying an extra digit everywhere. So now if I take the square root of the 65.333, that gives me 8.083, carrying one extra digit. Radians per second is omega. So now we've gotten K, which allowed us to get omega, and now we've got enough to actually write out the solution. But we need to use the initial conditions. Remember, always when you're doing a simple harmonic oscillator, the coefficient in front of the non-differentiated x variable, the square root of that is what is multiplied by the t in the a cosine omega t plus phi, and the a and phi are left to be determined by the initial conditions. In this case, they gave us the initial conditions. X0 is equal to the x at time t equals 0, and they said specifically that's negative 0.100, so negative 0.100 meters is equal to, this is supposed to be x evaluated at t equals 0. X at t equals 0 is a times the cosine of, now if you look at the solution, you realize when t is 0, the omega t term is 0, so this just becomes a times the cosine of phi. So we'll call that equation 1, and that's one of the initial value conditions. So again, whenever you're solving a differential equation, if it's a second order differential equation, meaning the highest derivative that you see in the differential equation is a second order, like this one is, x double dot, then you expect two initial conditions because, as you can sort of imagine, if you're solving a differential equation, you're trying to undo derivatives, and to undo a derivative, you have to integrate. And when you integrate without limits of integration, you introduce a constant. So if you have to integrate twice, you're going to introduce two constants. And in this case, that happens to be the a and the phi. So we don't really have enough information right now to figure out what part of this is A and what part of this is phi. So we have to use the other initial condition, which is that the velocity at t equals 0 is positive 0.400 seconds. Now we know that x of t is equal to a cosine omega t plus phi, and we've already shown you that if you take the derivative of that, you get v of t, and if you take the second derivative of that, you get acceleration as a function of time. But the main thing is we need the velocity as a function of time because that's one of the initial conditions they gave us. So when I take the derivative of x of t, I get the derivative of cosine is negative sine, so that becomes negative a omega sine omega t plus phi. That is our velocity as a function of time. So when I plug in velocity at t equals 0, the sine omega t plus phi just becomes the sine of phi. So in this case, we're now going to say for equation 2, the initial condition is positive 0.400 meters per second is equal to negative a times 8.083 radians per second times the sine of phi. So now we have two initial condition equations, and we can take sort of the best case scenario is to imagine dividing equation 2 by 1. So 2 divided by 1 gives us the following. We're going to say positive 0.400 meters per second divided by negative 0.100 meters is equal to the right hand side. So we did the right hand side, the left hand side of equation 1. We've done the left hand side of equation 2. Now we're going to take the right hand side of equation 1, or excuse me, equation 2, which is negative 8.083 radians per second times A times the sine of phi, and then all of that divided by the right-hand side of equation 1, which is A cosine phi. So the main thing that you see here now is that the A's cancel out, and that was partly why I chose to do the division, is the A's cancel out, and the sine theta over the, or excuse me, the sine phi over the cosine phi just becomes equal to tangent phi. So now what I've got is negative or positive 0.400 divided by negative 0.100 gives me just plain 4, and it actually should be a negative 4. And then on the right hand side, the A's cancel out, and I get a negative 8.083 radians per second times the tangent of phi. So what we have here is two negative numbers. Obviously, those two signs are going to cancel out, and we end up getting phi equals the tangent inverse of, now in this case, it's going to be 4.00 carrying one extra digit divided by 8.083, again carrying one extra digit, and the 8.083 is in radians per second, and the 4 was actually the point 0.4 divided by uh, zero point 0.1 was meters per second divided by meters. So that also could be the equivalent of radians per second because the units of radian is just a pure number. So if I take the inverse tangent of this, I can say shift tangent inverse of 4 divided by 8.083. And this is going to give me an angle, but it's not necessarily the final angle. The angle that that gives me is 26.32 degrees for phi, but what we got to remember is basically I had tangent of phi is equal to a negative divided by a negative. That means x and y were both negatives. That's the way the tangent function works. Or you could look back and realize that in equation 1, the cosine of phi had to be negative because a is automatically positive, and you had to realize that the sine of phi, you had to notice that the sine of phi had to be negative as well because there's no way to get a positive 4 on the left with that negative sign there. So sine and cosine are both negative. That again implies that we're at least in the second, or excuse me, the third quadrant. So what we have to do is add 180 degrees to this, and that would actually be what our phi is. So phi is actually going to be 180 degrees plus 26.32 degrees, which gives us 206.32 degrees. And of course, we don't normally express the phase angle in degrees, so we need to convert that to radians. But the main thing is we now have phi. So for part A, we have phi is equal to 206.32 degrees, and technically we only had three sig figs, so these three and this two as a bare minimum should be not significant. But now to convert that into radians, I'm going to multiply it by pi, and then I'm going to divide it by 180. So I'm going to multiply 206.83 uh, times pi. So it's 180 plus 26.3. Actually, that was supposed to be 33. I'll keep that, but it was really supposed to be 33. So I'm going to take the 206.33, multiply that by 3.14159 uh, radians, and then I'm going to divide that by 180 degrees. So I got 648.204 divided by 180 is equal to 3.601. So this is 3.601 radians, and that is our phase angle. So again, the part I messed up when I did this in class was I completely just dropped the 8.8083 and forgot to divide by it. So that's why I came up with a mistake. Uh, the other thing was I didn't mention to you guys to pay attention to your initial conditions to figure out what quadrant you're in, because the tangent function, for instance, when you take an inverse tangent, if you take it of a negative divided by a negative, it doesn't know whether the negative is in the numerator or the denominator, and depending on whether it's the numerator or denominator, it gives you a different quadrant. Additionally, if it's a negative divided by a negative, that's going to be the same as a positive divided by a positive, so you don't know if it's in the first quadrant or the third quadrant. So that's part of what you got to figure out. Now that we have that, we can go ahead and use, for instance, equation 1 to figure out what exactly is A. So using the phi and equation 1, we now have, oops, wrong color. We now have from equation 1 negative 0.100 meters is equal to A times the cosine of 3.601 radians with one extra digit. Of course, I'm not really going to use the radians. I'm going to use the 206.33 degrees that I had because my calculator is already in radian mode, or excuse me, already in degree mode. So I'm going to take cosine of 206.33, and that's going to give me negative 0.8962. So this quantity is negative 0.89625. And from that, I can solve for A by taking negative zero point 0.1 and dividing it by the answer that I just got. And that gives me A is equal to 0.1116 meters, and that's part B. So I can go ahead and put B here like this, and then I can box this off like that. So now we have the amplitude, and of course I actually added one extra digit beyond the sig fig, so I should underline that. Now all I have to do is say what is x of t, and of course x of t is just a cosine omega t plus phi, as we hypothesized for the solution of the differential equation. But now we actually know what a and phi are, as well as omega. So we'll say x of t is equal to 0.1116 meters times cosine of 8.083 radians per second times t plus 3.601 radians. So that's the actual x as a function of time. Sorry about having to split it over two lines, but I think that makes sense to everyone. Cosine of 8.083 in parentheses times time plus 3.601 radians. That too is inside the square brackets, and therefore it's part of the argument of cosine. But that was that problem. So